Welcome to the course module of speech signal processing. And in my previous lecture, we had already discussed about the autocorrelation method, in which we had calculated this autocorrelation matrix to get the values of predictor coefficient alpha case. And we had also calculated the minimum mean square prediction error En in the function of this particular autocorrelation function Rn. So now in this lecture, we have to see how the gain parameter of speech production model should be calculated. So here we have to see, this is the our speech production model that we had already discussed in my previous lectures. So here we had this one parameter G, which is known as the gain parameter of the model. So normally this gain parameter is associated with the amplitude of our excitation input. So in the case of voiced excitation, it will be a impulse train, and for the case of unvoiced excitation, it must be a random noise generator. So basically this gain parameter is going to decide the amplitude of these impulse train and random noise signal. So here it was the our transfer function of the vocal tract filter. So here we have this particular vocal tract time varying digital filter. So its jet transform or frequency response was given by this particular equation G upon 1 minus sum over k equals to 1 to p a k z to the power minus k. So here this ak was the filter coefficient. So we had already seen this expression. So if we cross multiply this equation and then if we take the inverse jet transform, so it can be shown that this Sn is going to be sum over k equals to 1 to p ak s n minus k plus g into un. So here, and this is Sn, which is the speech sequences, and here this un denotes the excitation input. So here we can write down this equation like GUN will be equals to Sn minus sum over k equals to 1 to p ak Sn minus k. So in my previous lecture, we had already defined this prediction error. So this prediction error En was defined as Sn minus S cap n, where this Sn denotes the present sample and this S cap n denotes the predicted value of the present sample. So this is predicted by the predictor, our linear predictor, right? So S cap n is the output of our linear predictor. So here we can write this Sn expression that we have already seen here. So this expression of Sn can be substituted over here. And then we can write this S cap n, which is equals to, which is the output of our linear predictor that we had already seen. It is k equals to 1 to p and alpha k s n minus k. So here in this case, you see, because here this ak denotes the filter coefficient of the digital filter, vocal tract digital filter, and these alpha case denotes you the predictor coefficients of your linear predictor, right? So if we assume that this a case are equals to alpha case, in that case, this first term and the second, this last term, a third term will get cancelled out. And this En is going to be equals to G into Un. So here we can see this prediction error En sequence, whatever we are going to get. If this alpha case and A case are both equal, then it is going to be equals to G into excitation. So here we can correlate these two things to get the values of G. So normally to get the value of gain parameter G, we are not directly comparing this equation, but what we do is we are actually calculating the energy of the excitation input signal, and we are comparing it with the energy of the error signal, right? So here we can make this comparison. We can calculate what will be the energy of excitation input. So here is the excitation input G into UN. So we have to calculate the energy of this particular input excitation input signal, and then it should be equated to the equal to the energy of our error signal En. Okay, so that will be denoted by, right, En. So here first we have to make the assumption, because in the case of voiced frame. Okay, if we have the voiced frame, in that case, normally the inputs is going to be the impulse train. Okay, so normally here we have to consider it to be a unit sample. So normally while calculating the gain parameter G for the voiced frame, this excitation UN is going to be, it will be considered as the delta n. Okay. So here we are considering it to be a unit sample, right? So here I'm just denoting it like unit sample, or you can say unit impulse. Okay. So here when this UN is equals to delta n, in that case, the response of the system. Okay. So this is our response of the system Sn. So whenever this UN is going to be delta n, because we are applying the unit impulse, in that case, the response Sn will be denoted by Hn, which is becoming the impulse response of the system, right? So here I can denote this Sn as the Hn, right? So we can directly substitute here this Un into this particular expression. So this Sn will be written as Hn, and this Sn minus k can be written as Hn minus k and plus G delta n. So now we have to solve this equation, okay, so as to get the values of G. So what is the method that we have to look here? So what should be the steps to get the value of G? So first of all, we have to define the autocorrelation function of Hn. So this is our impulse response. Okay, so this Hn autocorrelation function can be defined by this particular equation r cap m, which is equals to sum over n equals to 0 to infinity hn plus m. So here this is the definition of our autocorrelation function of Hn. So if in equation number 2, if we multiply both sides with Hn plus m, then this equation can be modified as this way. Okay, so this Hn multiplied with Hn plus m. So here within this summation, we have multiplied this term Hn plus m. Then here again, this multiplication of the Hn plus m has been done, right? So we obtain this equation number 3 just after multiplying this factor Hn plus m both the sides, right? So now one thing that we have to look after, what should be the result of this multiplication G delta n Hn plus m, okay? So since we are having here a delta function del n, right? So that we have to take care. So normally if you substitute m value equals to, because here you can, one thing that you understand, the Hn is going to be, for a causal system, going to be 0, right? So when at n equals to 0, we are applying any samples, then the response will be available only for n equal and 0, n equal to or greater than 0 values. Okay. So for n less than 0, the impulse response of the system must be 0. So that we have to remember, okay, because it is a causal system. So therefore, Hn equals to 0 for n less than 0, right? So here, if we are having m values equals to 1, 2, 3 up to p, in such cases, you can see here this impulse response will exist at n equals to -1, -2, and n equals to up to minus p. And therefore, if we multiply with this delta function del n, the product will become 0, right? Because this delta function will exist only for n equals to 0. And because this Hn plus m for these values of m is going to be 0, so this product is going to be 0, right? So this result is going to be 0. So here just we make this assumption that this m values is this range 1 to p. So in this case, what happens if you take this summation in both the sides of this equation number 3 with respect to n. So here just taking the summation over n from n equals to 0 to infinity. Here again in the right hand side also I have taken the same summation, and assuming that in this range of m, then this term in the right hand side will become 0, right? By just following this particular property, right? So we got this particular equation here. So if we further solve this equation, okay, so if we further solve, just we are rearranging the summation. Okay, so you can just we are just changing the order of this summation. So first we sum over from k equals to 1 to p, and I'm just writing this alpha k outside the second summation, and then here n equals to 0 to infinity Hn minus k into Hn plus m. Okay, so here one thing you can note down, that this left hand side is the definition of this autocorrelation function that we had defined here. Okay, so r cap m. Similarly, here you can see this term. This is also denoting you the autocorrelation function, and we had already seen in the autocorrelation method. Here both this signal hn minus k and hn plus m are actually having a certain relative shift. Okay, there is must be a certain relative shift. So normally in the autocorrelation function, only one function is getting shifted, but we had already seen in the autocorrelation method. Here, both the signals hn minus k and hn plus m will be getting shifted, and therefore the autocorrelation lag function will be the difference between these two sample index k and m. So therefore, this can be written as again as the autocorrelation function. So that autocorrelation function will be written as r cap mod of m minus k. Okay, so mod of m minus k. So it is the relative shifting between the two signals. It may be a advanced shifting, but it may be a like a delayed shifting. Okay, so that lag parameter, autocorrelation lag parameter will be mod m minus k. So those who are having any doubt about this equation, you please refer to my previous lecture where I had already discussed these things. Okay, so this equation has been replaced by this autocorrelation function r cap mod of m minus k, where this m values are 1 to up to p. Okay, 1 to up to p, right? So this is the autocorrelation function rm. Okay, so now if we go back to this equation number 3, and if we substitute m equals to 0, then here this left hand side will become hn multiplied with hn. And here in the right hand side, this equation will become hn minus k multiplied with hn, then plus g delta n hn. Okay. So because here it is getting multiplied with delta n, this product will become delta n into h naught, right? So now we have to think about what should be the value of h naught. Okay. So this h naught value can be directly be calculated from this equation number 2. So if you substitute for n equals to 0, then here you can easily show that this value, if you substitute, this will become h minus k plus g delta 0, right? So here delta 0 value is going to be 1 because it is a unit sample. So here you can see h naught, if you calculate, this first summation is going to be 0, because again we are following the same property because it is a causal system. For n less than 0, all these values is going to be 0, okay, because it is giving you h minus 1, minus 2 up to h minus p. So these all values are going to be 0, right? So here h naught is going to be 0. So now if we can substitute this value of h naught g into this particular equation, so if you substitute that, okay, and what we are doing is we are again taking the summation both the side with respect to n equals to 0 to infinity, right? The way we have done here, so we have to just make this summation. So if you take the summation both the sides, we will getting this particular equation here, okay? And then again, you can see here this I have just interchanged the order of summation here, and here this h naught I have substituted equals to g. So this will become g square, and here this summation will range from n equals to 0 to infinity delta n. So this value is going to be 1. So that 1 we can substitute there. So this equation here you can see it is hn multiplied with hn. So here m value is equals to 0. And therefore, this will be the autocorrelation function r cap 0. Okay, it will become r cap 0. So this is equal to sum over k equals to 1 to p and alpha k, and this will become r cap k, right? This will become r cap k. So just we are following this particular equation. Okay, so here the value of m was 0. So if you take the mod of minus k, it will become k, right? So this is r cap k plus g square. So this is our equation that we have got. So from this equation itself, we can calculate the value of gain parameter g. So here you can rewrite this equation g square, which is equals to r cap 0 minus sum over k equals to 1 to p alpha k r cap k. So this is our equation by which by using this equation, we can calculate the value of g. So one thing that you have to remember this, what this r cap 0 represents, okay? So this r cap 0 represents you the energy within the impulse response hn, okay? So here you see you must be aware about the property of the autocorrelation function. So if we have any function, let us suppose if it is denoted by Sn, then if you calculate the autocorrelation function for the signal Sn, then for correlation lag equals to 0, the autocorrelation value will give you the energy values, right? So therefore, this R cap 0 represents the energy of impulse response Hn, right? So this is your energy of the impulse response. So now again, you can just recall the fact that what we have said before, because this excitation un was taken to be delta n function for the voiced speech frame, and we called this Sn as the Hn. Okay, so this Hn is nothing but your speech sequences itself, right? So though we have just called it as to be impulse response, but obviously it is going to be your speech sequences only, right? So therefore, what we can say is this R cap naught, okay, which is denoting you the energy in the impulse response. It is also denoting you the energy in the speech signal, right? And therefore, this R cap 0 can also be written as R naught 0, Rn 0, okay? So here it can also be denoted you as the Rn 0. So you please recall in my previous lectures, we had already defined these terms, okay, before while discussing this autocorrelation method. And we had this equation for the minimum energy En, which is equals to Rn0 minus sum over k equals to 1 to P alpha k Rn k. So where this Rn0 we can got because the mod of I minus k here, you can see mod of I minus k will become 0, right? And therefore this Rn0 will be available, right? So this Rn0 denotes you the means energy of your speech sequence, right? Under that particular frame. Fine. So the same concept we have used here, because energy in the impulse response is also denotes you the energy in the speech signal, and therefore R cap n, R cap 0 will be equals to Rn0, right? Where Rn0 represents the energy in the speech signal SNM. Okay. Similarly, and this equation we had also calculated for the autocorrelation method, in which we got this particular equation while calculating the predictor coefficient alpha k, Rn mod of I minus k, alpha k equals to Rni. So if we compare this equation with this autocorrelation function of Hn that we had already derived here, okay, here you can see this particular equation number 4. So both the equations are similar, okay? A similar equation. Here this I was ranging from 1 to P. Again, this M is also ranging from 1 to P. And because both the things are same, so therefore what we can write is this R cap M, whatever we have written here, it is same as R and I, okay? So here we can write this R cap M is equal to R and M, okay? So we can have this, both the values are giving you the same result, right? So it means both the things are actually representing the same thing, okay? Because we just denoted this Sn as the Hn, and therefore it is again denoting the same thing Rnm, right? So basically what we can have this equation you can also rewrite in this form: G square equals to Rn0 minus sum over k equals to P alpha k Rnk. So here you just try to see this Rn0 is here, it is representing you the energy in the speech signal, okay? And here this R cap 0 was denoting you the energy within the impulse response Hn, which are both are the same things, right? So here you can easily see this equation we had already defined, derived in the autocorrelation method, and it was equal to the minimized energy En, right? So here just you have to get this minimized energy. So once you get the minimized energy, if you take the square root of that particular energy, that will be equals to your gain parameter G. So by just having this expressions, we can calculate this gain parameter G. So I hope you must have understood how to get this value of G. A similar analysis you can also make when the frame is unvoiced. So in that case, we have to take the particular white noise signal, okay, with a certain variance, okay, and then you can go on just solving the way I have done for the voiced case. You are going to get the similar kind of result. Okay, so please try out. Okay. So if you feel any doubt, if you having any doubt, let me know with your comments. So we'll stop here, and I will try to cover more lectures in few days. So thank you for watching this video. Stay connected with the channel.